Hi everyone, I'm Laurynas Lukas Kanopka, and this is my Milestone 3 report for the Algorithm Design and Analysis project. And I'm going to walk you through the vaults problem, the different problem variations, the greedy strategies, the naive recursion, and finally the dynamic programming optimizations. Alright, so let's first take a look at Milestone 1 and the greedy algorithms. First we tackled Algorithm 1, which solves a non-decreasing case for problem S1. Since the vault values get larger as you move to the right, our strategy was to start at the very end, pick the largest vault, skip back k plus 1 spots, and then repeat. And we proved that this is optimal using an exchange argument. So basically, swapping any choice with the rightmost available vault never lowers the total value, and this runs in efficient linear time. And then for algorithm 2, things got a little bit more difficult. Here the data starts high, drops to a bottom, and then goes back up. And our key observation was that the largest available values are always sitting at the edges of the list. So using a two-pointer strategy, I put one pointer at the start and one at the end, and in each step I just looked at which one was bigger, grabbed it, and then moved that pointer inward by k plus 1 spots to respect the distance constraint. And to prove this worked, I again used an exchange argument, and because of that valley shape, I proved that you can always swap the optimal choice for our greedy one without losing any value. So like algorithm 1, this one also runs in linear time. But when we moved over to the general problem where the data is random, greedy and the local optimum decision completely fails. So first, before implementing anything for algorithms 3 and 4, I went to LeetCode to practice the house robber problem, and it's basically the vault problem with a fixed k constraint of 1. So I did this so I could play around and have my implementations verified by all of the test cases that they have to make sure that I fully understood what I was doing before moving on to the assignment. Then I started with algorithm 3, which is a naive recursive approach, and it basically tries everything, and at every vault it asks, do we skip or do we take? So it gives the right answer, but the analysis shows that the runtime is exponential, and as you can see in my report, as soon as the input size hit 60, the runtime exploded, and I couldn't practically run tests past this value of n. So to fix this, we switched to dynamic programming with algorithm 4, and the core logic here is that the best score at any point is just a max of 2 choices, skipping the current vault or taking it. If we take it, we add its value to whatever the best score is, k plus 1 steps down the line, and we had to implement this in 2 different ways. So first was 4a, the top-down approach, and this uses a recursive helper function with memoization, and before computing anything, the function checks a memo table. If we've already solved this specific index, we just return the stored result immediately, which stops us from redoing any of the work. And then 4b was the bottom-up approach. So instead of recursion, I used a loop that starts at the very end of the vault list and works backwards to the start. We fill the table iteratively, so by the time the loop finishes at index 0, we have our answer built up from the subproblems. And now technically, both methods only visit end states, so you'd think that it would be fast, but the complexity ends up actually being theta n squared, and it's because in algorithm 4, every time our computer take decision, we're not just adding the numeric score, it's constructing a new list by copying the entire list of indices from the subproblem, which takes O(n) time, and adding the current index to it. So that's what gets us to the quadratic time here. And so that brings us to algorithm 5, which is the most optimal solution that we have in linear complexity. And to get this down to linear time, we had to stop copying those lists. So we split the logic into a 2-pass approach. For pass 1, you loop backwards and fill the table, but you only store the max score. And we don't touch any of the indices yet. So this makes it very quick because we don't have to copy over that indices list. And then once the table is full, we loop forward to figure out the path, and we compare the score at the current index with the next one. If they're different, we know that we must have took that vault, so we record that and then jump forward. So comparing algorithm 4 to algorithm 5, both algorithms use the exact same math, but algorithm 4 drags the entire history of choices along with it at every step, which makes it very, very heavy. Algorithm 5 is much more efficient as we only track the score and then figure out all of the choice history later, and that change drops us down from quadratic time to linear time. Okay, so we'll get to the live demo soon, but for the actual implementation, everything was done in Python. I used internal helper functions to keep the recursion clean in programs 3 and 4a. And for program 2, there was an interesting challenge of returning back the sorted list, which we obviously can't sort it at the end because that would be n log n complexity. So I used 2 separate lists and then just stuck them together at the end to avoid that. But the biggest headache was probably in program 4a. So the logic was fine, but Python has a default recursion limit of 1000. So when I tried running it on larger data sets, it crashed immediately with the recursion error. And to get around this and prove that the code is actually running fine, I had to import the system library and force the limit higher using sys.setRecursionLimit. And this made it work. So that was pretty good. And then for complexity analysis, for the plots, I used matplotlib and numpy, and for the mock data, I used the random library to generate random numbers that still match within our problem constraints. Okay, so let's actually move on to the implementation and the live demo. So as you can see here, I have all of the 6 different implementations, programs 1 through 5 with 4a and 4b, and then we have different inputs for different definitions of the problem. So we have problem S1, which is constantly increasing, and then we have S2, which is going to have a unimodal valley, essentially. And then we have the regular inputs and then a longer version of the inputs, just to show that our data works on more than one test case. So let's get started here. If we just look at the input of input S1, we can see that it's constantly increasing. And if we run program 1, we see that we get 120 and that we selected indices 1, 4, and 7, showing that our linear scan and greedy approach works. So now if we move on to algorithm 2 and we take a look at this data shape, we can see that the input starts high at 100, drops down to 1, and then rises back up to 90. And so we're greedily using 2 pointers to grab the massive numbers at the edges. So if we take a look at this one, we see that we get 191 and that it correctly identified the optimal path by converging from the outside in. Okay, now let's move on to our general cases with data. So if we take a look at input.txt, this is going to be example 1 in our PDF. And the good part about this is we know the answer to this because it's given to us. So if we take a look at our first naive implementation, we see our maximum value is 36 with decision indices 1, 4, and 7. And this lines up exactly with what we have in the PDF. And then we move on to top down. We see the same results, same correct answer. We look at our bottom up approach, same results. And then we look at our 2-pass linear optimization, same exact results. Now, if we move over to input 2, we see that this is example 3. Again, we also have the answers for this, so we can check if our programs actually work. If I run all of these, you can see that they all converge on a maximum of 38 with indices 1, 4, 6, and 8, showing us that it works with our test data. Okay, welcome back. Now let's look at some of the results from the experiments. So if we take a look at plot 7, it basically confirmed the analysis of what we did previously. The exponential algorithm just shoots straight up off the chart and basically isn't usable. Plot 8 was really interesting. It compared 4a and 4b, and even though they're both technically quadratic, the bottom-up approach was way faster because it didn't have all of the recursive overhead. And plot 6 proves that algorithm 5 is perfectly linear, and we can see that it handled 20 million elements in under 2 seconds. And finally, plot 9 showed us that the greedy approach on random data is consistently about 30% worse than the optimal solution, at least in my testing. So this shows that this just isn't viable. This will not get us the optimal solution. So in conclusion, this project let me really get hands-on with all of the concepts that we learned in class. So learning how to implement multiple greedy approaches, understanding the limitations of greedy, and then working with naive and then top-down and bottom-up DP implementations really let me internalize a lot of the concepts that we've been learning. I also learned that getting the recurrence relation right is only half the job in some cases, and that state management is really, really important as well. So what you store in your table matters just as much as the logic.